Okay. So thank you, dear and Blair, for inviting me here. So I will talk today about some unusual effects of on the vortex lattice when we look at the vortex lattice in very thin superconducting films. And I'm sure that the vortex lattice in film behaves somewhat differently than when we look at bulk superconductors. Okay, before I start, we have heard a beautiful talk by Sasepe on superfluid stiffness measurements. So there is a poster later on a new method to find the absolute value of superfluid stiffness from microwave measurements. But the talk today will primarily make use of scanning tunneling microscope to image the vortex lattice. So if you have a superconductor and you bring a tip very close to the surface and you take the conductance spectra, you get this typical superconducting conductance spectra which mimics the density of states. Now this is in zero field, but if you apply a magnetic field, then you will have vortices that thread like this. And if your tip is far from the core of a vortex, you will see something that is similar to this. However, if you bring it to the center of the core, then the center of the core is a normal metal, your tip is a normal metal, and you have a normal tunneling. So you will see something that is completely flat. That means that if I, for example, keep my bias voltage close to the zero bias and take a conductance map, then these vortices will manifest as local maxima in the image. If I go to this coherence peak bias voltage and then take a map, then these vortices will be local minima in the conductance map. For technical reason, we normally image at the coherence peak height, at the coherence peak voltage, and when you take over larger area, you then get these nice images of abricosal lab. This is on ideal diagonal. Now, the reason we are interested in this vortex lattice is that it's a very soft, tunable solid where you can actually change the areal density of vortex by applying magnetic field, by increasing magnetic field. So, magnetic field is somewhat equivalent to pressure in a real crystal. And there is this popular saying that vortex lattice melts like ice. What it means is that if you have a nice hexagonal vortex lattice like this and you increase temperature, it becomes disordered. And you can also increase magnetic field, which is equivalent to pressure here. It also becomes disordered. But there is a big caveat to this statement. And the caveat is that these states are not really liquid states. And we have imaged these lattices over 24 hours or longer. There is no dynamics at all when you take, let's say, an iodine diselenide single crystal, which is typically thick, about 100 micron or so thick. Now, what is known by now is that in conventional superconductors, thermal energy is never enough to melt the vortex lattice. And to understand this, we have to look at the energy scales of the problem. There is intervortex interaction, which promotes order, and thermal energy and random pinning energy, which promotes disorder. Now, if you take a bulk crystal, then both this thermal energy is actually insignificant. And if you take a very clean, let's say, bulk superconductor, a single crystal, where random pinning energy is also very small, then it has been shown that you remain in the abricosal vortex lattice, nice order, all the way up to H2. There is no order disorder transition at all. So when you have an order disorder transition, it's not caused by thermal energy, it's a competition between intervortex interaction and random pinning energy. The reason for that is that these vortices here are long vortices in the crystal, and they have a large condensation energy which is much larger than the thermal energy. The natural corollary to this would be that if I take a very thin superconductor, which is let's say a few nanometer, 200 nanometer thick, then the condensation energy will reduce by several orders of magnitude, and now thermal energy could become significant. Now, this we first studied in amorphous molybdenum germanium thin film. which we took a film of thickness of 20 nanometer, and it is also extremely low pin system. So it has a pinning which is about 5 orders of magnitude smaller than IBM, less than IBM pin. So here you have the interaction between intervortex, you have intervortex interaction and thermal energy. Pinning energy is a secondary role. This material gets oxidized very fast, so, and that's true of almost all these thin films. So whenever we do STM measurements on them, we do on in situ samples with this organic vacuum suitcase that never see atmosphere before we do the measurement. So, okay, when we did the measurement, here this is a 2 Kelvin. You can see with increasing magnetic field, the vortex lattice gradually disorders. But to understand if we have realized the true liquid state, or we are again in an amorphous state, we take this small window and keep imaging one after the other. So we take one image after another, and we track the trajectory of the vortices. Now in the solid state, you have just a small meandering motion of vortices here that you can see. If you go, for example, to high field, like 70 kilohertz state, here the vortices are in a liquid state and you have typically a random motion, the Brownian motion that you have read in school. However, if you go in between, you see something very different. Vortices are moving, but the movement is not random like this. They have preferential directions. And this is because we have here not only a very weakly, very thin, let's say, we have very short vortices, but we also have realized the 2D crystalline system. And a 2D system can undergo melting through 2 steps. First, going into a hexatic fluid, a fluid that maintains orientational order. So therefore, it can flow, but flow only along certain direction. And then this hexatic fluid in another transition goes into isotropic liquid. So this was actually predicted by Halperin, Nelson, and Young based on the Berezinski-Kosterlitz-Fowler's theory. However, one important point is that here, even though we have a liquid state, the vortex motion is very slow. So if you calculate the diffusion constant and try to estimate the resistivity if you pass a current, the resistivity is extremely small and you will never be able to measure such a small resistivity in an experiment. However, still there is a signature in transport. When you just measure resistivity, actually you see nothing. This is resistivity at 300 milli as a function of magnetic field. But when we do this measurement, we put filters to avoid external electromagnetic radiation to fall into your sample. And we can relax this filter. So when we relax this filter, you have external electromagnetic radiation that is going to your sample and that is exciting the vortices. This excitation does nothing in the solid state. Here the resistance remains 0. But in the liquid state, where the system is extremely susceptible to fluctuation, you can see that the resistance increases exponentially. Now I can do this measurement without the filter and actually look at these phase boundaries. Here, for example, this is a phase boundary between the solid to a hexatic transition. Here, this rapid increase here is the hexatic to the isotropic liquid. And now tracking this as a function of temperature, if I show you the phase diagram, you can see that in the phase diagram, I have only a tiny sliver of vortex solid. Most of it is this vortex fluid state, either hexatic or isotropic liquid. This was the first demonstration of hexatic fluid in a vortex system, but very soon after this, exactly the same sequence of transition was observed through Lorentz microscopy in Skyrmion lattices and later on rotating Bosch-Einstein condensers. Now there are, I think, even more reports of this. All right, this was a sample which was very, very weakly pinned, as I told you before. What if I go to the other extreme, where the intervortex interaction becomes secondary energy scale compared to pinning, because I increase the pinning. The way I increase the pinning is that I take another superconductor, which is amorphous rhenium zirconium, This is a new superconductor that was discovered during the COVID days in a collaboration between my group and Shungita's group. Now, here we also reduce the thickness to 5 nanometer to increase the effective pin. Now, when I show you here, at the same temperature and magnetic field, a conductance map for niobium diselenite crystal and amorphous rhenium zirconium. The main difference that you see here, each of these conductance minima corresponding to vortices have the same intensity. Here, on the other hand, you can see that some of them are very deep and some of them are very shallow. The reason that happens is this. So look at this cartoon of a conductance map here. If I am taking an image, if I bring the tip here and take a conductance spectra, I will see this nice superconducting spectra. On the other hand, if I now move the tip where I have a vortex, maybe meandering around its main position a little bit, then most of the time the vortex core will be below my tip, and both this gap will be strongly suppressed and the coherence peak will be suppressed. However, if I bring the tip here, where the vortex is jumping between these two sides, the tip will see the vortex core only 50% of the time. So I will get something in between these two. So when I take a conductance map at coherence peak bias, the intensity of the conductance minimum actually reflects the amount of time the vortex spends at a particular location. In other words, it's like a probability density map. So this idea actually came from this paper, the density functional theory of flux line that is melting, which is an extension of the famous Yusuf Ramakrishnan density functional theory of melting applied to vortices. All right. So now having this image here, I can first determine the conductance minima. I determine the nearest neighbor by Delaunay triangulation, and then using a criteria, I find this motion path of these vortices. So these are by these blue lines. I join this quick minima along which the vortices are moving. Now, I also do not take one image, but we take at least 10 or 20 images successively at the same field and temperature, at the same location. And you can see that these motion paths are also changing from frame to frame. So over a long time, the motion path will be the linear superposition of all these motion paths that you see here. But there is something more to the story. If you look at this minima here, some of these minima, like these ones in red, these are deep minima that remain the same in all images. But if you look at these images in circle in green here, some of these minima, they change position, and also this minima change intensity. So this is the first, third, and seventh frame of the sequence. And what is happening is this. What I have considered earlier was this complete hops. A vortex jumps from one deep minima to another deep minima. But every once in a while, there is a possibility that during this jump, I have an incomplete hop and the vortex is trapped in an intermediate local pinning potential. And then, because you have vortex interaction, this would change the landscape. So in the next image, this will become the dominant pinning minima, whereas here, this will become the subdominant one. Now, this is what we call incomplete hop. And to find the motion due to incomplete hop, we take all these images again and we just sum these images. Now, when I sum these images, you can see these streaks. This is along which the vortices are moving due to this incomplete hops.
Yeah. May I ask, if you take one of the picture of the top, not the average one, if you sum up all the vortices, you have a conservation of magnitude?
We have about 10 to 15% extra minima. Because
okay, so then it's the movement. Okay.
Yeah, very good question. So I can now actually use some criteria and form this motion path from incomplete hops. And now the global motion path will be the sum of incomplete and complete hop, which is this. Now, when I do this for a 5 nanometer film, how much time do I have? Okay. So when I do that for a 5 nanometer film, what I see is that even in presence of strong pinning, I never realize a vortex solid, either crystalline or amorphous. It's always remaining in this inhomogeneous liquid state. However, now let me go to the situation where all these energy scales compete with each other. None of them can be ignored. For that, what I do is that I take the same film, rhenium zirconium, and I increase the thickness to 20 nanometer. Now, this was the very weakly pinned sample. This was the somewhat strongly pinned sample. Now I go to this intermediate pinned sample. I do the same measurement. 460 millikelvin, I start with a very inhomogeneous vortex liquid at 3 kilo I increase the magnetic field, and by 20 kilo you can see I have almost a completely ordered solid. Then I increase magnetic field again, and it melts again into this inhomogeneous liquid. So, if I can do various metrics, look at the fraction of vortices that are connected to motion paths. I can also measure the metric of orientational order. All of these are consistent. But this is not the most interesting part of the story. The interesting part of the story is this. I have to go to 3 kilo state now. Here I have an inhomogeneous liquid at 460 millikelvin. I increase to 2 Kelvin. By the time I go to 3 Kelvin, I have nearly completely ordered solid. Now 3 Kelvin, when I increase to 4 Kelvin, it abruptly melts. This is possibly the regular first order melting transition. And here I cannot identify the minima, so I am just showing you the image. At 20 kilo state, it's already ordered, so little happens. At 30 kilo state, it is the high field disordered state, and it goes from a liquid to more liquid and so on. So what we are, okay, now here I have shown you this with a lot of analysis, but suppose you don't want to believe any of the analysis, you take only the raw images. I have 20 images in a row, and you just add the raw images without any filtering. What you see is that when the vortices are moving around, it has a very low contrast. I increase the magnetic field here, keeping the temperature constant. At 20 kilo state, I have a solid. So here the contrast builds up. And then at higher field, it again melts. I can do the same thing as a function of temperature, keeping the I can do it as a function of temperature, keeping the magnetic field the same. And here you see at 3 Kelvin, you have a completely ordered solid. So what we are seeing there is a phenomenon called inverse melting that was actually predicted by Gustav Tammann more than 100 years ago, but not observed in his lifetime. And the most well-known example of this is liquid helium-3, where you have this Pomeranchuk instability, where you can see if you are at 3 megapascal, you go and you increase temperature, you go from a liquid to a solid and then back to a liquid state. The same thing was actually predicted for vortices, I think first by David Nelson and then by many others. However, there has been very few experimental confirmation of this. There was one experimental confirmation of this from a-Re6Zr from thermodynamic measurement, but here they could never really get a liquid state. So they had to continuously shake the vortices with a dithering field. Now we know that sand also flows if you shake it, but sand, whether it's a liquid or not, I leave it for your imagination. Now, we can also construct the phase diagram, and for the phase diagram, we use all these anomalies associated with the phase transition in transport and magnetic shielding measurement. I am not going to too much of details of this. And with this is the phase diagram that I have. I have a liquid state here, going into a solid state here, and then again a liquid state here. More interestingly, this happens only at an intermediate range of pinning, typically for the 20 nanometer thick sample. When I am at 5 nanometer, it's all a liquid. And when I am at 50 nanometer, here I just go from a solid to a liquid with increasing magnetic field or temperature, and I have no inverse melting. So this inverse lattice is actually a competition between these three energy scales, which needs to be investigated further. Now, with the very short time that I have, 5 minutes, I can. Whatever I have shown you so far was actually essentially classical physics. These are classical phase transition. But let's ask the question, the vortices, are they actually classical objects or do they have a quantum nature associated with it? Now, if these have quantum nature associated with it, then one of the signature would be 0-point fluctuation, the quantum 0-point fluctuation. For this, we do a careful spectroscopy of the vortex core. Now, if you take a very clean superconductor, for example, a very clean niobium diselenide, you will see that away from the core you have the gap. At the core, you can see a small peak which is called the Caroly-Rosen-Matricorn peak, which is because you are confining the normal electron within the size of the vortex core, the normal core. However, this is very sensitive to disorder, and if you take, for example, a slightly more disordered crystal, then this will get washed out and you'll get something that is completely flat inside the vortex. These two behaviors are understood. However, when we took a molybdenum germanium film and we did this measurement, what we saw is that inside, at the center of the vortex core, I can see a soft gap and I can also see a coherence peak, this black one here. This is far away from the vortex core, the purple one. This is not easy to explain. And our conjecture was that vortices are actually not static at their equilibrium position, but they are actually jumping around a little bit. And if I put my tip here and if I had a very fast measurement probe, I would see this fluctuating kind of spectra. But SCM is a very slow measurement. So what I will see is something which is averaged out. So even at the vortex core, I will see something like this. The question is this fluctuation from thermal or quantum origin? Now to understand this, I have to find out the amplitude of fluctuation with respect to the vortex lattice constant as a function of magnetic field. So for that, we actually simulate the conductance map. So we have a scheme to interpolate between, let's say, a flat spectrum at the center and a spectrum like this, which is identical to the zero field, far away from the vortex core. And we interpolate this with a Gaussian in position that has a full width of half maxima, which is twice the coherence length. Now, if you do that, you simulate this kind of zero bias conductance map, and this is without any fluctuation. Here, my vortices are not fluctuating at all. When I have to simulate for fluctuating vortices, what I do is this. I displace each of the vortex by a small amount, which both in their direction and in their so both in direction and angle. So this the displacement is between a random number between 0 to delta A, and of course the direction is 0 to 2 pi, again taken as a random number. Now we make about 200 such replica and sum them. So this is in some way the Born-Oppenheimer approximation. And then this is what you see. Delta A by A is my relative amplitude of fluctuation. Here it is 0. As I increase the fluctuation, you can see that it gets more and more blurred. And if you look at the conductance now, you will see that at the center of the vortex, you have a conductance that does not go to 1. So this is my zero bias conductance, and this is the conductance at the coherence peak height. To check whether this works, for example, we take, let's say, this data at 450 millikelvin and 30 kilohertz. I simulate the conductance map with a delta A by A. Delta A is the amplitude of fluctuation, and A is my vortex lattice constant of 0.275. And now you can see if I take the zero bias conductance map and I take this line cut, which I show here by this red, and the experimental data is this blue one, where I have summed these three line cuts and taken the average, they match extremely well. When I go to the coherence peak bias, they match in amplitude, but there is a difference in the absolute value, which is probably because I am ignoring the effect of circulating supercurrent. Nevertheless, we can now take this zero bias, the variation of the zero bias conductance passing through the vortex core, and from there, by fitting this, I get this delta A by A as a function of magnetic field at 450 millikelvin. The question is that, does this represent classical or quantum fluctuation? For this, we do a very simple theory where this under a harmonic approximation, we find out what would be the amplitude of thermal motion versus 0-point motion when you distort the vortex lattice a little bit. And the main takeaway from this is this. For thermal motion, there will be no magnetic field dependence of delta A by A. It will depend only on temperature. And for 0-point fluctuation, the quantum 0-point fluctuation, delta A by A would be given by this quantity, which will go as magnetic field to the power 1/4. So, this simple calculation, actually, we realized that it was done earlier by a-Re6Zr and his collaborators with a much more sophisticated way, taking the full dispersion. But the difference with our result was only a factor of 0.7. And this is now the final result. You can see that this red line is h to the power 1/4. It matches qualitatively reasonably well. And you can take this prefactor and now calculate what would be the vortex mass. The vortex mass turns out to be 36 electron mass. And if I take the theoretical estimate of the vortex mass, this is the most popular theoretical estimate. There are many other estimates though. We get about 32 vortex mass, which is very consistent. We also see that omega naught, which is the resonant frequency, that depends to some extent, that depends on magnetic field, but it varies from hundreds of megahertz to about a terahertz over, let's say, 1 kilohertz to 100 kilohertz. And I end here, so I will not describe this at all. I think our result was one of the first results where we showed in a superconductor the vortices having a quantum nature. But there is this very recent result that this paper that I would like, and all of you can read this, where they have actually shown quantum coherent manipulation and readout of superconducting vortex state, which to me is a complete confirmation of the quantum nature of the vortex. Okay, I don't have any time to describe that. This is the summary, but which I will not read. And these are the collaborators. Thank you. One or two questions, maybe? Yes.
Thank you. Yeah, thank you for that talk. I have a question regarding checking whether it's quantum or thermal fluctuations. Would it be possible to just follow the temperature dependence of the fluctuation?
Yes.
I assume the simulation was
Yes.
was a zero temperature.
It is. So you can do that, and we tried that also, but it's much more complicated because at high temperature you lose contrast typically in STM spectroscopy. So for comparison, we check between 450 millikelvin and 2 Kelvin. We could not do high. And you can here you have a crossover field if you calculate the quantum and classical fluctuation. The crossover field is about 10 kilohertz if you go to 2 Kelvin. And you can see at high fields, there is not much difference between the quantum and classical fluctuation. But when you go to low fields, particularly below 10 kilohertz, there is a very large difference between the two. The thermal fluctuation here actually is taking over the quantum fluctuation. But this is to some extent not completely convincing. This is the only data we have at higher temperatures.
Lower temperature, then more than 50 is your base temperature. Okay.
Yeah, we work with helium.
So the transport regarding the inverse melting, so I wonder if you see any indication in the transport.
Yeah, we did. Okay. I rushed through this, but indeed we see, and that is what I am showing you here. So you see the melting of the vortex lattice, we use this phenomena which is called a peak effect. Peak effect means whenever you have an order to disorder transition, you have an anomaly in the critical current. An anomaly in the critical current will reflect in every other property. It will reflect in magnetic shielding response, it will in resist susceptibility, in resistivity. So for example, here you see, this is the melting transition. Melting means a higher field transition. And here if you measure resistance as a function of temperature at a current which is close to a critical current, instead of going monotonically, you have this anomaly here. And this is what we track, for example, to make the phase diagram. The inverse melting is much more difficult to capture. What we found out is that you can capture it if you measure the shielding response and look at the dissipative part of the shielding response. Now, the dissipative part of the shielding response should monotonically decrease with temperature, like this black line here. Instead, it shows you this anomaly here. And this anomaly, you see, you can see only up to 20 kilohertz, because above 20 kilohertz, it's already, you don't have any inverse melting transition. So, you can see here. So, you see this anomaly only up to, let's say, this field here. So, at higher fields, there is just one transition from solid to liquid.
So it doesn't manifest as the resistance.
Hmm.
Okay, maybe we can discuss.
We can discuss later.
Yeah.
Thank you very much, Pratap. Thank you very much, all the speakers. I remind you, we have 2:30, we come back here for the talk by some people.